So in this video we're gonna start chapter number 7, which is changes of state and the gas laws. So in this chapter we're gonna talk about what are the different states of matter and then how these states can be converted into each other, right? Like solid can convert into a liquid, liquid can convert into a gas, and we're gonna talk about these changes. And later on we're gonna talk about the gases law, the properties of the gases and how these properties affect the behavior of the gas. So let's get started and let's go to the new slide. So these are the content of this chapter or this PowerPoint. In the first section 7.1 we're going to talk about the changes of the state. In the other section we're going to talk about the property of the gases and the gases laws. And the last one we're going to talk about what are gas mixture and what is partial pressure. Okay, so now let's get started with our first section, which is changes of state. So we already know about there are 3 states of matter. We already discussed previously in the previous chapter. What are those? If you remember, there are 3 states of matter. They can be solid, liquid, and gas. So in this section we're going to talk about how these different state of matter can be converted into each other, right? So this is called changes of state. So a substance in one state of matter changing into another states of matter. For example, solid can convert into a liquid, liquid can convert into a gas, and vice versa. They can go backward. Gas can be converted into a liquid and liquid can be converted back into a solid. And there is one more changes that can happen, where solid can directly convert into a gas without the inclusion of liquid in between, or a gas can directly turn into or convert it into a solid, right, without going through a liquid phase or right state. So let's take an example that is given on the right side in the picture. Let's start with the solid, that is ice. So what's happened? Solid ice can be converted into a liquid, right? And this process of converting an ice, which is a solid form of water, a solid phase of water, into a liquid water, we call that as a process called melting. So melting is a process where a solid converted into a liquid. And what's the opposite process? If I want to convert a liquid into a solid one more time, the process is known as freezing. Similar, so these are 2 phase change from solid to liquid and coming back from liquid to solid. So make sure you know this definition, melting as well as freezing. Then we have, if I convert liquid to a gas, then the process we call this change of state, and the process for converting this changes from liquid to gas we call as vaporization or an evaporation process, right? And to convert back a gas or a steam, sometimes we call a steam, right, in the gas phase if we talk about a water. So we can convert a gas again into a liquid form, which is liquid water, through a process called condensation. So make sure you remember this thing. Evaporation is the opposite of condensation, where in evaporation liquid goes to a gas phase, in condensation gas come back into a liquid form. And there is 2 more terminology over here, which is sublimation and deposition. What is sublimation? So sublimation is a process where a solid can directly convert it or take a phase change into a gas phase. So solid is directly going to a gas phase. We call this process as sublimation. And then if the gas can directly come back again in a phase change to a solid, we call that process as deposition. So this process is deposition, right? So make sure you know all the definition, all the all the processes in this diagram, because this will be helpful. Okay, so now let's go to the next slide, and then we're gonna talk about more about all these processes. So these are the processes that we already talked about on the previous slide, but to have an idea one more time, let's talk it one more time. So the solid phase is going to turn into a liquid. We call that as melting, right? Or a special term called fusion. We're gonna talk about this thing later in the chapter. If the liquid goes to the solid, we call this process as freezing. Liquid to gas, vaporization or evaporation, we already talk about. From gas to a liquid phase, a condensation process. And if the matter which is in solid directly converted into a gas phase without going through a liquid, we call that process as sublimation. And the last one, if that gas is directly converted back into the solid without again going through a liquid phase, we call as deposition. For example, for sublimation, this is an example. If you can see this picture on the right hand side, this is a solid carbon dioxide. So if you can see, this is a solid, and then the whitish thing you're seeing, this is a solid carbon dioxide, and the vapor is coming out from here. So that means a solid is directly converted into a gas phase. So this is an example of sublimation, right? so make sure you know this definition, right? So now let's talk about how the three states of matter are different from each other. So if we talk about solid, liquid, and gas, how these three states of matter are different. So they are different according to the kinetic energy that they have, or the atom or the molecules they have, right? For example, in solid, the atoms doesn't have a lot of kinetic energy because the atoms are so tightly packed, compared to the liquid where you have a little bit more kinetic energy compared to the solid. But in the gas, the atoms has the highest kinetic energy because the gas atoms are moving like randomly, right? and how they are also different depending on the intermolecular force of attraction between the atoms in these states of matter: solid, liquid, and gas. So in solid, the intermolecular, so what are the three intermolecular forces that we already studied in the previous chapter? So we have dispersion force, then we have hydrogen bond, and then we have dipole interaction, right? Dipole forces. So we're gonna see how the intermolecular forces are different in different states of matter. In solid, we have the atoms are so tightly packed, that means they have a strong intermolecular forces compared to the liquid, and gas has the smallest or weakest intermolecular forces between the atom because the atoms are so far apart, right? So we have solid, liquid, and gas. So let's assume this way: at a given temperature, the kinetic energy of all the atoms which is present in liquid, solid, or gas have to have the same kind of kinetic energy, because the kinetic energy depend on what? The temperature of that particular matter, right? So I can say temperature is directly proportional to the kinetic energy of the atom. That means if the temperature increase, the kinetic energy of the atoms also increase, right? Because you are providing more heat. But in solid, even though the atoms are not moving compared to the liquid, right, and in gas, the atoms are moving fast at the same temperature. So why is the case? So it depends on the intermolecular force of attraction. So in solid, there is a strong intermolecular force of attraction between the atoms, so that even though they have the same kinetic energy, the force of attraction is so high that the atom cannot move around at the same temperature. Where in liquid, the intermolecular force of attraction is a little bit lesser or smaller or weaker, you can say, compared to the solid. So that's why the atoms in the liquid will have a little bit more kinetic energy or more motion of the molecule, right? And then in gas atoms has the weakest intermolecular forces because the atoms are so far apart then the gas atoms are not not get attracted between the other atoms, and then they are like moving freely. So that's why at the same temperature, gas atoms or molecule has the highest speed of the atom, means higher kinetic energy, because this atom has the weakest intermolecular forces, right? So there is no one to hold the atom together. So make sure you know this concept. And the intermolecular forces of attraction, we know depending on the element on the compound. Ionic compound will have dipole or hydrogen bond, or non-polar might have dispersion forces. So it depends on the element of the compound that we are talking about, but this is a general idea. So now let's try to get this picture that is given on the right side of this slide. So we have a solid, 3 states: solid, liquid and gas. And then it's been showing that the intermolecular forces of attraction are increasing going from gas to solid, right? Because the atoms in the solid are so tightly packed, we already discussed on the previous slide. And then if we go from solid to gas, the kinetic energy of the atoms is going to get increased, because there is no more force of attraction, the intermolecular force of attraction in the gas molecule. That's why there is no force to hold the atoms like together. So intermolecular forces, we can say, are formed or disruptive during the phase change or the change of the state. So if I want to convert a solid into a liquid, I need to disturb the intermolecular forces that is present within the solid, so that the atoms doesn't get the same kind of force of attraction like we have in liquid. For example, if I have to convert solid to liquid, I have to break the intermolecular forces between the solid atom. That's why the atoms will be a little bit further apart. And if I want to go from liquid to gas, I have to break the intermolecular forces that is already present in the liquid, so that we can still make the atom a little bit more further apart. That's the case in gas, right? And how we can get the atoms in the liquid to move to get them separated like a more, by breaking the intermolecular forces between them, right? So remember this thing. So during a change of state, the intermolecular force of attraction are usually formed or disturbed. So we just talk about how we can convert a solid to a liquid or liquid to gas by disrupting the intermolecular forces between them. We can do the same thing in an opposite way. If I want to convert a gas into a liquid, what's the process? Condensation, right? Then what we need to do? We have to move the atoms, or we have to increase the intermolecular forces of attraction in the gas particles, so that they can convert into a liquid, right? So in condensation process, which is a conversion of gas to liquid, you are forming a new force of attraction, or you are strengthening the force of attraction between the atom. And same thing apply from liquid to a solid, that is freezing, the process called freezing. So in the same thing, you are increasing the intermolecular force of attraction in liquid, so that liquid can convert into a solid form, right? And then all these changes are physical change. We are not changing the atom, or we are not converting an atom into a different atom. We are just doing a physical change, right? And the last thing that you need to remember, the covalent bond, that is the bond present between the molecule to make a molecule, or between the atom, are not changed. For example, water, right? The covalent bond between hydrogen and oxygen in water is not going to change if the water is present in a solid form or a liquid form, or they are present in gas. So water is still H2O. So make sure you remember this concept. So now we're going to talk about mainly on solid and liquid phases. So we know in solid and liquid phases or state of matter, the force of attraction are stronger between the atoms that make up the solid and liquid. So the strongest intermolecular force of attraction that a compound can have is mainly that have the hydrogen bonding in them, because hydrogen bond is the strongest intermolecular force that we already discussed in the previous chapters. And we already know what is the requirement of the hydrogen bonding. The hydrogen has to be connected with the oxygen, nitrogen, or a fluorine, right? So, and then if any polar molecule that have these conditions already met, they can make a hydrogen bond, and then they can have a strong intermolecular forces, and they usually exist in the form of liquid or a gases, not liquid and solid, not in the gases form, because they have strongest intermolecular forces between them. So let's take an example of ethanol and propane. Let's assume they have the same kinetic energy, means if both of the molecule is present at the same temperature, right? If I provide the same temperature, that means I'm providing the same kinetic energy for both the molecules, right? And let's see what's the states or the phase of these two molecules at the same temperature. For ethanol has an OH, the hydrogen attached with the oxygen, so they can make a hydrogen bond. So this is the strongest intermolecular force of attraction, so they can occur in liquid at that temperature, because at room temperature that energy or that temperature is not strong enough to break the hydrogen bond, right? But for propane is a non-polar compound, and because of its non-polar nature, they form a dispersion force of intermolecular interaction, right? And dispersion force is the weakest intermolecular forces. So if I provide a temperature even at room temperature, this temperature is enough to break the intermolecular forces, which is dispersion forces between the propane, and then the compound is present mainly in the gas phase, right? So this is how the intermolecular forces affect, and then will tell you whether the given compound is present in a liquid or solid form or a gas form, depending on the strength of the intermolecular forces that they have. So now let's talk about the energy transfer and then how it affects the change of state. So previously we already talked about that if the matter is going to change the state from solid to liquid, that means there is a change in energy or the temperature. Why? Because in solid the intermolecular force is so strong, the atoms are so closely packed. In liquid the atoms are a little bit far apart. So that means if you provide enough energy to the atoms or molecule in solid so that they can break the intermolecular forces, they can enter the liquid phase. So that means you have to provide the energy, or the energy has to come from the surrounding to the solid, and then if that energy is enough to break the intermolecular forces, they can convert into a liquid phase. So that means during a changes of state, there is a transfer of energy either from the atmosphere or the surrounding to the matter, or from matter to the surrounding. You can say surrounding, right? So we're gonna see how the energy is moving from the matter to the surrounding, or from the surrounding to the matter, right? So we already talk about heat energy transfer to or from the surrounding, right? So one of the process called vaporization, if you remember what is vaporization, to convert a liquid to a gas phase, that we call as vaporization. So we can write over here liquid state goes to a gas state. So what happened during this? So that means the liquid atoms in the liquid form has a strong intermolecular forces. The atoms are very close to each other, but in the gas phase they are very far apart. That means that some energy has to be provided by the surrounding to the liquid so that they can break up the intermolecular forces present in the liquid, right? And the atoms can get free and convert into a gas phase. So that means an energy has to be transferred from the surrounding to the matter or the substance that is being evaporated, right? So what happened during this energy transfer? You increasing the kinetic energy of the liquid molecule, because if you're providing a heat, you are increasing the temperature, and we know increasing the temperature, increasing the kinetic energy of the molecule of that particular state, right? And the energy of the liquid molecule increases, it break up the intermolecular force of attraction between them, and molecule then enter into a gas phase. So remember this thing, in evaporation, energy transfer from the surrounding to the matter. And which kind of reaction is this one? This is an endothermic reaction. Right, because the energy is being absorbed by the liquid, right, to convert into a gas phase. So evaporation is an endothermic reaction. So now let's talk about like different processes that we discussed on the previous couple of slides at the beginning of this PowerPoint. We learned about 6 processes: melting, evaporation, sublimation, freezing, condensation, and deposition. And we're going to talk about in which process the energy or the heat is being absorbed, in which other processes is being released to the environment or to the surrounding. So for heat absorbed from the surrounding, whenever we do a melting, because what is melting? Melting goes from solid to a liquid. So that means energy has to provide it to a solid to break its intermolecular forces between the molecule to convert into a liquid, right? That's why energy being absorbed. What is evaporation? We already talk about from liquid to a gas phase. We still have to provide some energy to break the intermolecular force in liquid. And what is sublimation? It is going from solid state to a gas phase. Again, you have to provide the energy, or the surrounding has to provide the energy to the solid before it can convert into a gas with the weakest intermolecular force of attraction, right? Now let's talk about in which processes heat is normally get released to the surrounding. In freezing. So what is freezing? Freezing means when liquid convert into a solid form, right? For example, ice. When you freeze a liquid in like water, it converting into an ice, which is solid form. So what happened during this thing? So liquid has the highest energy in the molecule, right? It has the weaker intermolecular force because the atoms are have high kinetic energy. They are moving fast compared to the solid. So what's need to be happen? So extra energy that you need to release from the liquid so that the atoms doesn't have enough energy to move around and then can stick together, or they have the intermolecular forces are strong enough to hold the atom or molecule together. That's how they can convert it into a solid form. It has to release that extra energy, right? So that means that extra energy is releasing to the environment, right? Same for condensation. Condensation is from gas to a liquid. Again, in gas, the atom has high kinetic energy, means the intermolecular force is not strong enough to hold the molecule together, so that extra energy has to get released, because if you release extra energy, that means you are decreasing the kinetic energy of the molecule, and now the atoms are not moving fast enough, and the intermolecular force can hold those molecules together, right, to convert into a liquid form. Same for deposition. Deposition, gas directly convert into a solid. Same process, same concept. Energy has to get released from the gas state so that they can convert into liquid. So all these processes are exothermic processes. They are exothermic. And then the top 3 where the heat get absorbed, they are endothermic reaction. So make sure you know this concept. And one more thing which is important, during an endothermic reaction, the surrounding is getting cooler. So I can say the surrounding getting cooler. Why does the surrounding is getting cooler or get lower in temperature? Because the heat is transfer from the surrounding to the matter. So you're decreasing the temperature of the surrounding. Same thing in exothermic reaction, you are heating up the surrounding, because you're releasing the extra energy to the surrounding so that the temperature of the surrounding is getting increased, right? That means the temperature of the surrounding is getting increased too. So yeah, so this is the concept that you're going to remember from this slide. So now we're going to talk about a special property of the gas called compressibility. So gases are compressible, means you can compress the gas. If you provide enough pressure, you can lower down the volume of the gas, right? So it says under sufficient pressure, gas molecule undergo a change of state from gas to a liquid. Because what happened when you apply pressure? Because if you apply pressure, the volume of the gas is going to go smaller because you are providing a lot of pressure, and during this pressure the gas is going to convert into a liquid. So that's why the gases are compressible. For example, if you already seen this kind of oxygen cylinder with any person that has the lung problem, which is difficult for that person, the breathing is difficult, then they usually hold this kind of oxygen cylinder, and then in this oxygen cylinder the oxygen gas is present in liquid form. Why? Because this oxygen gas is compressed with a high pressure so that the oxygen gas is converted into a liquid oxygen, and liquid oxygen need a smaller volume compared to a oxygen gas in a gaseous phase, right? So that's why all these oxygen are compressed or pressurized in a small volume in a liquid oxygen. So now we're going to talk about two important terms called melting and boiling point, and then we're going to learn about what does it mean. So boiling point is the temperature at which a substance undergo phase change from liquid to gas. So boiling point is that temperature at which there's going to be a phase change from liquid to a gas. And then what is melting point? Melting point is the temperature at which a substance again goes from the phase change but from solid to a liquid form. And then boiling and melting point are the temperature at which temperature you're gonna see these phase changes from liquid to gas for boiling point, from solid to liquid for melting point. And all these temperature or the major thing are happening at normal atmospheric pressure, right? And then the normal atmospheric pressure is 1 atmosphere. We're gonna talk about this thing later on. Atmosphere is the unit of pressure, but make sure you know this definition, melting and boiling point. So now we're gonna talk about a curve or a graph called heating curve. And what is heating curve, we're gonna learn about on this slide. So heating curve we normally use to get the melting point and the boiling point of a substance through a graph. So if you can see on the graph on the right hand side, you can get the melting point and the boiling point of that particular gas or the solid using this graph, right? So this graph normally tells you on the y-axis is a temperature which is keep on increasing. The x-axis normally tells you how much amount of heat is being added, right, to the matter in calorie. So the heating curve shows how the temperature of a substance increases or remain constant as heat is being added, right? The second one, horizontal plateau, represent change of state at constant temperature, and the third one is heat is absorbed for a phase change instead of increasing temperature. So we're going to learn about all these three lines that we just talk about using a graph. So if we can see, let's talk about a solid. Let's talk about an ice. Ice is a solid, and then if I add the heat, so if I go across the x-axis, we are adding the heat, and if we are adding the heat, that means we are increasing the temperature, right? So the temperature goes from -30 to 0, and at 0 degrees Celsius the ice start melting. And if we keep on adding the heat, then that means the rest of the heat is not going to increase the temperature of this ice. It normally being used to melt all the ice that is present, right? That's why you have the plateau over here, right? And once it reaches the end of the plateau, this is the point. This point is your melting point. Means at this point all the ice that is present is already melted and is present in the liquid form, right? So if you can see over here, so this has been named as delta H of fusion, how much energy you require to melt a solid into a liquid. So once the ice is getting converting into a liquid completely, now if I add more heat, that means now the heat is going to be used to raise the temperature of that liquid, right? Now you can see, now the temperature is around 100 degrees Celsius. Now if we reach this point, this is your boiling point. So at this point the molecule start boiling, and now if we keep on adding the heat, that heat is going to use to break all the bond, the hydrogen bond that we have in a liquid, so that the liquid can convert into a gaseous phase. So this extra heat after the boiling point is now be getting used to break all the kind of intermolecular force of interaction that is present in the liquid form. And then if you can see, then the temperature of this liquid is not getting increased anymore during this process. So this process we call as delta H of evaporation. So remember, that's why you have an plateau, the straight line, because the temperature is not increasing. We are getting the heat, but that heat is getting used to get all the intermolecular force interaction, right, to break all of them. And once you break all the force of interaction, now everything is in gas phase over here. And if I provide more heat, then the temperature of the steam, this is a gas phase, which we also call as steam, right? If we add more heat, that means you are increasing the temperature of the steam. That's why the burn using a steam is much severe than the boiling water, because steam has more energy in there, that has more temperature compared to the boiling water, right? If you can see from the graph. So this is how this heating curve work, and then you can get the melting point and boiling point if you already have the heating curve in front of you. So yeah, so make sure you know how to interpret this heating curve. And then similarly, like we have heating curve, we also have the cooling curve. But the difference is, for cooling curve, it start from the steam and it goes back to the ice form, right? We're gonna talk all the cooling curve on the next slide. So let's go to the next slide. So this is a cooling curve. It's gonna be exactly the same or similar to the one that we just saw on the previous slide, but it start with the gas phase, which is steam, and it record, because we are doing cooling, so the temperature has to decrease and heat has to get removed from each phase change. So it goes from steam to liquid, liquid to solid. So every time you're gonna release some heat, right? So whenever the gas or the steam convert into a liquid, this is called as condensation, and it occur at boiling point. And then from liquid to solid, we know this is freezing, and it happens at melting point. So make sure you know this thing. And then I think that should be it for the heating and cooling curve. Let's get to the next slide. So now we're going to talk about two terms, heat of evaporation and heat of fusion, and then we're going to learn about what these terms are. So let's start with the heat of fusion, symbolized with triangle delta H of FUS, means heat of fusion, right? So it's the amount of energy required to melt a 1 mole of a solid at its melting point. So you can say 1 mole of a solid. So how much energy required to melt a mole of a solid at its melting point, right? So the heat of fusion is an endothermic reaction. Endothermic reaction because you are providing the heat to convert a solid into a liquid. Similarly, the same amount of heat energy might be released, or you need to remove the same amount of energy if you want to freeze a liquid into a solid again, right? So it's the same thing. So remember, heat of fusion is the amount of energy required to melt a 1 mole of a solid, and what is freezing is the same amount of heat energy is going to release from a liquid before it convert into a solid, right? So freezing is an exothermic reaction, right? But heat of fusion, endothermic. The other term that we're going to talk about is heat of vaporization. As the term is saying, vaporization means converting from liquid to vapor. Is the amount of energy required to boil a liquid at its boiling point, or you can say amount of energy required to convert 1 mole of liquid into a vapor phase. And so what is heat of vaporization? Heat of vaporization is also an endothermic reaction because you are providing energy to convert a liquid to a gas phase. But when you convert a liquid, the gas again back to a liquid form, you have to remove the same amount of energy, and this process we call as condensation, right? And condensation is an exothermic reaction, right? It's the opposite of heat of vaporization. And now if we talk about which thing is bigger, which if you have heat of fusion, heat of vaporization, which term is bigger? So heat of vaporization is always bigger than heat of fusion. Why? But what happened during heat of vaporization? So you are breaking up all the intermolecular force of attraction between the molecule. Why? Because during heat of vaporization you're converting a liquid into a gas phase. And why the atoms and how the atom is going to go from liquid to gas phase? When they break every force of attraction between them, so you need more energy. Whereas in heat of fusion, what is heat of fusion? When you're converting a solid into a liquid. So while you're doing solid to liquid conversion, you don't have to break all the intermolecular force of attraction. You need to break like a certain amount of intermolecular force of attraction, because the atoms are still in contact. Not as much in solid, but in liquid they're still in contact, right? They have still some kind of intermolecular forces, but in gas there is no intermolecular forces, which is heat of vaporization. So your heat of vaporization is always bigger than heat of fusion. So remember this thing. So this is a table that's showing up several melting, heat of vaporization, heat of fusion, melting point and boiling point of some of the substance. So we have aluminum, ethanol, water, carbon dioxide. We have delta H of fusion, vaporization, the melting point and boiling point. If you see about over here, if you see water, the heat of vaporization is 539. So that means that is 539 calorie per gram. So that means you need to have 539 calorie of energy to convert 1 gram of liquid into a gas phase. So this is heat of vaporization. And for water, heat of fusion is 79.5. That means you need to have 79.5 calorie of energy to provide to convert ice into a liquid form, to melt a solid to a liquid form. So this is how you can get the number for different substances. So now let's try to do some problem on the basis of the concept that we just discussed. So the problem says, for each of the change of state, given the term associated with it, and then label it an exothermic or endothermic reaction. So the first problem says if the state changed from gas to a solid. So now we know this is from the gas to solid without going through a liquid form. This is deposition. And the gas is coming back to a solid form is an exothermic reaction, because energy has to get released to the atmosphere or to the surrounding before atom can come close together, right, in the solid form. Second one is solid to liquid. We know is a melting, and melting is an endothermic reaction because you need to provide energy to break the intermolecular forces between the atoms in the solid before it converting into a liquid form. The third one is liquid to a gas form. So this is, we know, is evaporation because you're converting liquid to gas, and whenever you convert a liquid to gas, you need to provide energy, right? So this is an endothermic reaction. So this is how you can solve or write the endothermic or the process's name depending on the phase change between the states of matter, you can say. So now let's try to do one more problem. It says how much heat in calorie are required to convert a 10 gram of liquid water at 100 degrees Celsius to steam at 100 degrees Celsius. So that means it says how much energy. So you're going from liquid to a steam. What is steam? Is a gas, right? So you're going from liquid to gas. So it's saying how much energy you need to provide to that 10 grams of liquid before it converting into a steam. So we know, so what is this? This is vaporization, or you can say heat of vaporization, right? And we are assuming, right, and we know this is liquid water, and we know for heat of evaporation for a water is 539 calorie per gram from the table that we just discussed on the previous slides. This is a heat of evaporation. And how would I know this is a heat of evaporation? We already talk about because it's going from liquid to gas. And then if it's 539 calorie per gram, I can say for every 1 gram of water to convert from a liquid to a gas phase, I need to provide 539 calorie of energy. And from this I can make a conversion factor. We need calorie, so 539 on the top and 1 gram on the bottom. So this is the conversion factor they got. And then grams get cancelled, and then when you multiply you get this 5380 calories. So that means you need to provide this amount of energy to convert a 10 gram of liquid water to a steam. So make sure, depending on the substance that is given in the problem, in this case it's water, it can be ethanol or any kind of substance, the heat of evaporation, you need to have this equivalency or this number before you can solve the problem based on that, right? So always convert this number into an equivalency and then use a conversion factor to solve the problem. So now we're gonna talk about the term called specific heat. And before we go to the specific, we already talk about the melting point and the boiling point. So there's one more physical property, like we have melting and boiling point, we call as specific heat, right? And then this specific heat is determined by the strength of intermolecular forces. Means how much intermolecular force you have in that particular matter determine how much specific heat you have for that matter, right? So specific heat is a physical property that reflect the ability of a substance to absorb heat. That means how much amount of heat energy that particular matter or particular state of matter can get or cannot absorb without changing its temperature, right? So for example, some substances like solid, liquid or gases normally absorb different kind of energy without getting change in their temperature, right? So let's say how we can define the specific heat. So specific heat of any substance is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, right? And then what's the unit of specific is calorie, grams per degree Celsius. And we're gonna talk about what is the equation, what formula we use to get the specific heat in the next slide, right? So let's go to the next slide, and then we're gonna talk about more about the specific heat over there. So before we go and talk about the equation of the specific heat to calculate the specific heat of any matter, So let's talk about this table. So this is the table showing you the specific heat for different substances. So for water, the specific heat is 1 calorie per gram per degree Celsius. For ethanol is 0.5. For water in the solid form, 0.490 calorie per gram per degree Celsius. So similarly, you can get the specific heat for different substances, and the specific heat is constant for different matter. So is a property of the matter, or the of the matter, right? Whether it's in liquid, solid, or gas. Now let's talk about the equation that we normally use to get the specific heat, right? So this is we call as heat equation, and then the equation is heat equal to specific heat calorie per gram per degree Celsius, the unit, over mass multiply by the change in temperature. So let me tell you one more time. So specific heat is the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So what happened when you, let's take an example. If you have any substance, a solid substance, and right now the temperature of this substance is 25 degrees Celsius, right? And the amount is 1 gram. This is 1 gram of solid matter. So how much heat energy, so let's say if I ignite this thing, how much heat energy we need to provide to this matter so that the temperature of this matter is going to change from 25 to 26 degrees Celsius. Is what's the change? 1 degree Celsius. So different substances might absorb different amount of energy before it can raise its temperature by 1 degree Celsius, right? And it depends on the specific heat of that particular matter. So for example, one more example. So let's say if you have two matter A, matter B, right? And then both the matter are present at 25 degrees Celsius, and both have the same amount, 1 gram. And if I provide the same amount of energy to heat up this both matter, let's say if I put 5 calorie of energy for both of them. So let's, after a couple of minutes, the temperature of A changed from 25 to 26 degrees Celsius. It changed by 1 degree Celsius. But after like several hours, let's say 1 hour or 30 minutes or more than the amount of time that I provided for A, the temperature of B is still not increased by 1 degree Celsius. It still is at 25. So let's say after an hour, 1 hour, the temperature goes from 25 to 26 degrees Celsius. So that means the specific heat of B is higher compared to specific heat of A, because by the definition of specific heat is the how much energy you require to change the temperature of 1 gram of substance by 1 degree Celsius. So that means if you put the 5 calorie of energy for B for a longer period of time, that means you are providing more energy to B before it can change its temperature by 1 degree Celsius. So that means the specific heat of B is higher compared to specific heat of A. So this is how you can compare the specific heat of multiple matter. So remember this thing: if the specific heat of any matter is bigger compared to specific heat of, let's say, any matter B, that means you need more energy before the temperature is going to change of this matter. So let's say we talk about B, let's say B over here, not A. This is your A because I use the symbol A and B over here. So we know specific heat of B is bigger than specific heat of A. So that means you need more energy before it rises the temperature by 1 degree Celsius for B compared to A. So make sure you know this concept. Higher the specific heat, more energy required. And then again, let's go back to the equation. Equation is heat. We normally show heat in the form of symbol Q. Specific heat is S, mass we normally say m, and what is delta T means? Delta T is your change in temperature, and it always final temperature minus initial temperature. Always, it doesn't matter the temperature come out to be negative or positive, it doesn't matter, make sure it always final minus initial, right? And in degree Celsius. So the formula come out to be Q equal to ms delta T. So we're gonna do some problem based on this equation and then try to learn how we can use this equation to solve the problem. So let's try to solve this problem. It says calculate the heat required to raise 45 grams of liquid water from 23 to 32 degrees Celsius. So that means if this is the mass of the matter is given, which is liquid, this, and the temperature is going from 23 to 32. This is your initial temperature, 32 is your final temperature. Once the experiment is done, it says how much energy you need to provide so the temperature of the matter increases, right? And we know the formula Q equal to ms delta T, and first we have to figure it out what is delta T. So delta T is gonna be Tf minus T initial. Final temperature is 32.0, my initial temperature is 23.0, and the number come out to be 9.0 degrees Celsius. This is how you get 9.0. And then the specific heat of water, liquid water, is always 1 calorie per gram per degree Celsius, and this is a constant number for liquid water. So if you go back to that table that we just saw, that showing you the specific heat of different matter, you can get this number from that table, 1 calorie. So now let's plug in the number. What's the mass? 45 grams. What's your specific heat? 1 calorie per gram per degree Celsius, that's the unit. And what's the delta T? Delta T we just calculated is 9.0 degrees Celsius. So grams get cancelled, degree Celsius get cancelled, and if you multiply these number 45 times 1 times 9, you're gonna get around 405 calories. So this is the amount of energy that you need to provide before to 45 grams of liquid before it can get heated up from 23 to 32 degrees Celsius. So this is how you can use the equation of the specific heat. Yeah. So now let's get to the second section of this PowerPoint, which is where we're gonna talk about the properties of the gas and then the gas laws. Right? So now let's get to the next slide and then start with the properties of the gases. Okay, so now we're gonna talk about the gases. So we're gonna talk about the gas at the molecular level, and the theory that tells about the behavior of the gas at the molecular level is kinetic and molecular theory, or we can say kinetic molecular view, and it describes the behavior of the gas at molecular level, right? How the atoms are behaving in the gas. So it says 3 things about the gas. The first one is the gases, atoms and the molecule are in constant motion and moving at high speed. So greater the speed means greater the kinetic energy and higher temperature, means if the atoms of the gas molecule are moving faster, if they move faster, they have higher kinetic energy, and we know the kinetic energy of any matter is depend on the temperature of that matter. So that means higher kinetic energy, higher temperature of that gas molecule. So remember this thing. The second thing, it says the gases, atom or molecule always move in a straight line in random direction. So if the gas molecule is moving, they don't go in a zigzag manner, they always go in a straight line but in random direction, and collide with the walls of the container and fill entire container. Means if you put the gas molecule or the gas in a special container or in some kind of container, the atom or the gas molecule are moving in a straight line in random direction, and they're gonna collide with the inner surface of the container. And then what's the volume of that particular gas is the entire volume of that container. And the third one is a gaseous atom and molecule are far apart from one another and they don't have any intermolecular force of attraction, and we already know this thing, right? We already discussed about this thing on the previous slide. The atoms of the gas are so far apart, there is no force of attraction between the atom, and if they don't have any force of attraction, they won't be like sticking together. So these are the three things that the kinetic molecular normally told or uses for his theory. So now let's and make sure you know all these three concepts, because we're gonna use all these assumptions in this section of the lecture. So now we're going to talk about a pressure, because the gas molecule are moving randomly, right, in a space. If we put a gas in a container and the gas molecule or atoms are moving randomly with a higher speed, there is a chance that they're going to collide with the inner surface of the container, right? And then if they're colliding with the inner surface of the container, they're going to provide some kind of force to that container, right? For example, if you see on the right hand side, let's assume this is a cross-sectional view of one side of the container, and these are the atom of the gas molecule that is filled up in that container. And then if they're moving fast in a straight line, there's a chance they're gonna collide with the surface and then return back and bounce back, right? And what's happening over here, every time they bounce on the container, they're providing some kind of pressure, some kind of force to that container. And then how we're gonna calculate how much pressure they're providing to the inner surface of the container? We know the formula. Pressure is force per unit area. If I know the force, how much force they are exerting on the surface, and if I know the area of that particular cross-sectional surface, we divide both them and we can get the pressure, right? So remember this thing, pressure is force per unit area, and then the pressure of the gas is also depend on the temperature. If we don't change the volume of the gas container, so if you increase the temperature, what's going to happen? You are increasing the speed, the kinetic energy of the atom of that particular gas. And if the kinetic energy is going to increase, there's a more frequency, there's a high chance that the atoms are colliding with the inner surface of the container much faster compared to one that when they have less amount of kinetic energy. So if you increase the temperature, you are increasing the pressure of that gas, right? Because you are forcing the atom to collide with the inner wall or inner wall of the container much faster or much quicker compared to the one if they don't have high kinetic energy. So make sure you know this concept too, to get an idea how you're going to determine the pressure. And if we only talk about the pressure, now let's talk about the unit of the pressure, right? If we need to measure the pressure, we need to have the unit, right? So the main unit that we're gonna use is atmosphere, and we're gonna use this atmosphere to convert different unit of pressure, right? So one of the important units is atm. So if we have any number written in the form of atm, that means we are measuring the pressure of that particular substance. And then we have some other unit too, milliliter of mercury. If you have of mercury, that means we are measuring pressure. Then we have torr, we have psi and pascal. All 5 units belongs to the pressure, and they just show you how they are interconnected to each other. So that means if I say I have 1 atmosphere of pressure, that means it can be have 760 of mercury, or I can say is equal to 760 of torr in different unit of the pressure, or I can say I have 14.70 psi of pressure, same thing, 101.325 pascal. So if you say 1 atmosphere, or if you say 760 torr, psi, pascal, they have the same meaning. And then from here I can get one equivalency, and from equivalency I can use a conversion factor to convert 1 unit of pressure into a second unit of pressure. For example, if I give you an example over here, if I have 780 torr, how many atmosphere I have? How you gonna do it? So we already know I can write 780 torr, and then we know 1 atmosphere is equal to how much? 760 torr. Can I make a one conversion factor? Yes, I can make. Put 1 ATM on the top, put 760 torr on the bottom. Torr get cancelled, and if you divide these two numbers, you're gonna get around 1.03 ATM. So that means I can say 780 torr is same as 1.03 ATM. So this is how you can interconvert different unit of pressure. Right. So this is an example. Make sure you know how to convert, and then make sure you know how to use an equivalency and convert into a conversion factor. Okay, so let's get to the next slide, and then now we're going to learn about the atmospheric pressure and then the barometer, right, and the instrument that we normally use to measure the atmospheric pressure. So what is atmospheric pressure? We know air is a mixture, right? In atmosphere we have an air, and it's made up of 78% nitrogen, 21% of oxygen, and we have some other gases too, carbon dioxide, argon, water vapor, right? So air is a mixture of all those things, and because the air is present on the surface of the earth, because of this composition is going to provide some pressure on the surface of the earth, right, and which we call as atmospheric pressure. And what is atmospheric pressure? Is the force of air molecule pressing on earth due to gravity. And then we usually take at sea level, the atmospheric pressure is 1 atmosphere. So this is standard. We normally use 1 atmosphere. At sea level, that pressure is always 1 atm. Now we're gonna see how we can get this 1 atm, right, on how we're gonna use the barometer, the instrument that we're going to use to measure the atmospheric pressure. Let's talk about this thing on the next slide. So barometer is an instrument that we normally use to measure the atmospheric pressure at sea level. So this instrument, it consists of an inverted glass tube, right, and then we have a mercury that is filled in the plate on the bottom, and then we have inverted glass tube that is already inside the plate that have the mercury. If you fill that plate with full of mercury liquid, Hg, and then what's gonna happen, because outside this glass tube and outside this plate that has the mercury filled in it, we have atmosphere, right, and because of atmosphere we have atmospheric pressure, right, and this atmospheric pressure going to press this mercury liquid, and then because of this pressure the mercury will go fill out this glass tube on the top, and we're gonna see how much the mercury level rises during this process. And at sea level it rises to 760 mm, and we know 760 mm is 1 atm, right. So is the amount of the level of the mercury rises during the experiment in this inverted glass tube that normally tells what's the atmospheric pressure at that particular location, right. Higher the atmospheric pressure at that particular location where you're using the barometer, the higher the length of the mercury in that glass tube compared to where you have lower atmospheric pressure, you will get lower increase or less increase in height of the mercury in the inverted glass tube. So this is how you can measure the atmospheric pressure at different location. So now let's take an example about the atmospheric pressure at different height. So at higher altitude you always have a lower atmospheric pressure, right, like the top of the Mount Everest, right, any hilly area, because you always have a fewer molecule pressing down, right, because you have less amount of the air present at that particular location. And if you have a less pressure, that means you have less atmospheric pressure over there, means you have less amount of air present, and if you have less amount of air present, you have less amount of oxygen. And that's why you always carry an oxygen cylinder along with you whenever you're going like up to the mountain, or you're climbing up the mountain, because the air pressure or the oxygen pressure is lower at that height. Now let's take an example. Why do people who climb Mount Everest usually carry cylinder to the oxygen? We already talked about this thing on the previous slide, because the atmospheric pressure at high altitude has less oxygen, because you have less atmospheric pressure over there, and because of that you will always have difficulty in breathing. That's why the extra oxygen that you get from the cylinder always useful. So now we're gonna talk about the gases law. But before we go to the gases law, let's talk about what are the 4 different variables or parameters that we need to study before we can either predict the behavior of the gas, or say what the gas is going to do, right? What's the property of the gas. So the 4 variables are pressure, volume, temperature, and the number of moles, the amount of the gas. And now we're gonna talk about how these 4 parameter is going to tell you about the property of the gas by using all those 4 in the form of gas law. So now let's try to do a talk about some of the simple gases law that normally take into account only 2 variables out of the 4. So we have 4 variables: pressure, volume, temperature, and number of moles. So the simple gas law normally talk about any of the 2 factor and see how these 2 factor affect the behavior of the gas, how they are connected, unless the other 2 are remain constant, they don't change, right? So different gases law uses different 2 variables to see the behavior of the gas, and then they make the other 2 variable constant, right? So the first law that we're going to talk about is the Boyle's law, and it tells you about the relationship between pressure and volume. And then if they talk about the pressure and volume, then the temperature and the number of moles has to remain constant. These 2 things doesn't have to be changed, right? So this Boyle's law says pressure and volume are inversely proportional as long as you don't change the number of moles and the temperature of that gas. So I can say pressure is inversely proportional. What is meant by the inversely proportional means if one thing goes up, another thing goes down, right? So if we increase the pressure, the volume will decrease. If we decrease the volume, pressure will increase. So this is inversely proportional. The second one we're going to talk about is a Charles law. Charles law tells you the relationship between volume and temperature. So if we're talking about volume and temperature, then pressure and number of moles has to remain constant. So this law says volume and temperature are directly proportional, means volume is directly proportional to the temperature. Means if one thing goes up, another thing goes up. They are directly related, right? And vice versa. One thing goes down, another thing should go down. The third law that we're going to talk about is Gay-Lussac law, and this law normally tells the relation between pressure and temperature. It says pressure is directly proportional to the temperature of the gas molecule if the volume and the temperature remain, where if the number of moles and volume are constant, right? So that means directly proportional. Again, if you increase the temperature of the gas, you are increasing the pressure of the gas, because they are directly related. So we're gonna talk about these 3 things individually and then try to learn what these laws are and then talk about more. So now on this slide, what you're looking at, this slide show you the simple gas law diagrams, right? And then the first diagram that you're seeing over here is Boyle's law. So Boyle's law we know is pressure is inversely proportional to volume, right? So that means if one thing goes up, another thing should go down. So if you see y-axis as pressure, x-axis as volume, then you will get this kind of graph. But if you make a graph between pressure and 1 by v, which is directly related, 1 by v and p, then you get a straight line, right? Similarly for Charles law says volume is directly proportional to the temperature. That means if volume increase, temperature increases, right? So that means it's also a straight line. And Gay-Lussac law again, pressure directly proportional to temperature, pressure increase, temperature increase, again is a straight line between pressure and temperature, right? So this is how you can make a graph. So now let's talk about first about the Boyle's law. Boyle's law tells you about the pressure and volume, and we already talk about pressure is inversely proportional to the volume. And and if I open this equation, we're gonna get something like this: pressure is equal to kV. K is your constant, and then if I multiply by both sides by V, you're gonna get PV equal to K. So that means multiplication of pressure with volume, you will always get a constant number. For example, let's take an example: 2 times 4, you get 8, right? So this is your pressure, this is your volume, and then this is your K. So the constant number is K. So if I decrease the pressure, let's say by 1, now the pressure is 1, what should be the volume, so that this number won't change? The volume should be 8, so that the number is still is 8, right? PV, pressure times volume. So what's happened over here, if you decrease the pressure by 2 times, what you're having over here, you're increasing the volume by 2 times, so that you get the constant number every time, right? So this is the law, says pressure times volume will always get you the constant number. Now we have an equation, we can get an equation: P1 V1 equal to P2 V2. P1 V1 are the initial volume and pressure, P2 V2 are final volume and final pressure, as long as the number of moles and temperature remain constant. So this is the equation we can use to solve the problem on Boyle's law, or you can use the same problem, right? This is the same equation, but instead of 1 and 2 it says I and F. I is initial, F is final, so it's the same thing. Okay, so let's take an example on the right hand side that you can see over here in the picture. Let's assume if we have 1 atmosphere pressure on the top, and then the volume of the gas over here is, let's assume this is 4 liter. Right? If I increase the pressure from 1 atmosphere to 2 atmosphere, then what should be the volume then over here? How you gonna get? So what happened over here? I increased the pressure from 1 to 2 atmosphere. So according to the Boyle's law, the volume should decrease by the same factor. So I increase the pressure by 2 times. So the pressure should decrease by half, right? So 4 by 2, 2 liters. So that's your final volume, because the number has to be the same. 1 times 4, 4, 2 times 2, 4. The constant number is same. So this is how you can figure it out. You can also get an example of the Boyle's law during breathing or exhaling. When we inhale the air, the lungs, the diaphragm underneath our lungs expand. If they expand, it increasing the volume, right? So that means it can take more air. But during an exhale, the diaphragm contract, means it increases the pressure, decreasing the volume of the lungs. If you're decreasing the volume of the lungs, then pressure has to increase. If the pressure is increasing, you get exhale gas, you exhale the gas. So this is how the breathing work, right? So at pressure in lungs decreases, air flow in, pressure in lung increases, gas flows out, right? So Boyle's law normally tells about this breathing too. So now let's try to do this problem. The problem says a helium balloon with a volume of 1.1 liter and the pressure at 1.1 liter is 0.91 atm expand to 3.1 liter after being taken into the mountain. What's the new pressure, assuming no change in temperature and gas? So the initial pressure P1 is 0.9 atm. Always write the given value. What's your initial volume? V1, 1.1 liter. What's your final pressure? You need to figure it out. Final volume after expanding is 3.1 liter. So we have, and then this equation this problem belongs to the Boyle's law. How would I know? Because the pressure and volumes are given. It's already saying temperature and the number of moles of the gas is constant. So there is only one law, Boyle's law, that apply all those things. So P1 V1 equal to P2 V2. We need P2. So P2 V2. P2 will be P1 V1 over V2. And when you plug in the number over here, so V1 is 1.1 liter. V1, let's take this out. So pressure is 0.91 atm. V1 is 1.1 liter over volume 2 is 3.1 liter. Liter get cancel it out. Then your final answer will be 0.32 atm. So that means your pressure will be, the final after the gas expand is gonna be 0.32 atm. And it makes sense because the volume increases. So if the volume increases, then the pressure should be lesser than 0.91, which is 0.32, right? It makes sense. So this is how you can cross verify your answer too. Let's try to do one more problem. The pressure gauge on the patient's full 10.7 liter oxygen cylinder read 8.5 atm at constant temperature. So temperature is constant. How many liter of oxygen can the patient tank deliver at a pressure of 0.92 atmosphere? So volume is given, pressure is given, initial one, right? So this is your V1, this is your P1, and it says how many liter, that's your V2. You have to figure it out, and your P2 is 0.92. So you have to use P1 V1 equal to P2 V2, and then you have to figure it out V2 gonna be P1 V1 over P2. And when you plug in the number 8.5 for P1, 10.7 for V1, 0.92 for P2, you're going to get 84 liter. Because pressure decreases, that's why the volume must increase in, right, according to the Boyle's law. Now let's talk about the second law, which is a Charles law. And we already know the Charles law normally tells the relationship between the volume and temperature of the gas. We know volume is directly proportional to the temperature. Again, the same thing. If you remove this proportionality sign, you will get one constant K with T. Divide both sides by T. You're gonna get V by T equal to constant. So the ratio of volume over temperature is always a constant number. So from here, I can again get some equation that we normally used to get the problem solved. So I can say from here, I can say V1 over T1 equal to V2 over T2. Again, 1 and 2 are initial and final, is the same equation that we have over here. So you can use I or V1 over T1 over V2 over T2 as long as number of moles and the pressure are constant, right? And the most important thing that you need to remember always, temperature is always been Kelvins. You cannot use temperature in degrees Celsius or Fahrenheit whenever you are solving any problem on the gas law. Your temperature always has to be in Kelvin. If any other units are given, convert that into a Kelvin first and then plug in the value of temperature. Right, so let's take an example. On the right side you have a picture. This says you have a gas enclosed in a container. At the initial condition, the temperature of the gas is 200 Kelvin. Let's say the volume of this gas is 1 liter. If I heat this gas and the temperature goes from 200 to 400, how much time we increase the temperature? We increase the temperature by 2 times. That means the volume of this temperature also has to increase 2 times because they are directly related. The volume is 2 liter then. because volume is directly related to temperature. One thing goes up, another thing goes up with the same thing, right? So this is how you can predict the behavior of the gas in Charles' law. So let's try to solve some problem on this Charles' law equation and then see how we can use this equation to solve the problem. So the problem says a 19.5 liter of sample of neon gas is cooled, this is important, from 76 degrees Celsius to 38. So the temperature is going down. What is the volume of neon in liters at this lower temperature, assuming the pressure is constant? So we have to use a Charles' law because there's a relationship between volume and temperature, and it says the pressure and the amount are constant. So we know this is your V1, 19.5, this is your T1, this is your T2, and you have to figure it out V2, what's the volume, right? And we know before we use an equation V1 over T1 over V2 over T2, or you can say VI, TI, VF, TF, we have to convert the temperature into a Kelvin first, because the temperature in degrees Celsius. So if temperature is 76 degrees Celsius, that means it's equal to 349 Kelvin, because we know Kelvin is equal to degrees Celsius plus 273. Similarly, the final temperature, which is at 38 degrees Celsius, that means we have 301 Kelvin, and we need to use this temperature in Kelvin. That's why we convert it. And we need V2, so I can reshuffle this equation to get VF. So VF is gonna be VI times TF over TI. So like I said, I means initial and F means final. So plug in the number, Kelvin cancel, then your final volume come out to be 17.4. And if you can see, during this experiment, the temperature is decrease. If the temperature decrease, volume has to decrease, because volume is directly related to temperature. That's your Charles' law. Okay, now let's talk about the third law, Gay-Lussac law. Gay-Lussac law says pressure is directly related to the temperature. Again, the same thing. If you remove this proportional sign, you will get KT, and then divide both sides by temperature. You're gonna get P over T equal to a constant. So that means the ratio is constant, and we can get from here to here Pi Ti over P of Tf, or I can say P1 V1 equal to P2 over T2. Same thing, right? As long as number of moles and volume are constant, right? So if you can see on the right hand side, there's the same picture that normally tells you about the Gay-Lussac law. You have a gas enclosed in a container that has a temperature of 200 Kelvin. Let's say the pressure is P, and if the temperature increase from 200 to 400, that means you are increasing the temperature 2 times, and the pressure will become 2 times 2P, because they are directly related. Because while increasing temperature, you are increasing the kinetic energy of the molecule. If you increase the kinetic energy of the molecule, there is a high frequency of atom to bounce back from the inner container, means you have high pressure. So this is how the Gay-Lussac law work, as long as number and moles and the volume of the gas are constant. So now let's try to do some problem on this concept on the next slide. So the problem says, before leaving, your tire pressure, car tire pressure is 35.2 psi, and the temperature of that air in your tire is 25 degrees Celsius. After driving, the tire pressure came out to be 36.5, and what's the new temperature of the air, right? So it was given pressure given, temperature given. So we have to use the Gay-Lussac law, right? This is the only law that uses pressure and temperature. So this is how you can determine which law we have to use to solve some of the problem. So we know Gay-Lussac law is this, and let's see what we have given. So initial pressure is given 35.2, initial temperature was given 25 degrees Celsius, final pressure was given 36.5, and then you're gonna calculate for final temperature T2, and we know T2 is your TF. You can say T2 or TF are same. So your final temperature, the equation come out to be TF is equal to final pressure minus initial temperature divided by initial pressure, and then plug in the value. But before you plug in the value, again check your temperature has to be in Kelvin. So we already talk about how to convert in Kelvin. So 25 degrees Celsius 298.15, right? So and then plug in the value. PSI will cancel out, and then your final unit is Kelvin, and when you solve this thing, you're gonna get that 309.16 Kelvin. And then in the problem it says the pressure increase from 35 to 36.5, so temperature has to increase, because according to the law they are related to each other directly. So that's why the temperature is higher, final temperature, compared to the initial one, which is 298. Okay, so we already solved the problem, but let me tell you how you're gonna get this equation from the given relationship, right? So if you have to take TF, there is a way called cross multiplication way. So the rule says whatever unit that you need to figure it out always has to be on the top, right? And then everything else on the other side. So this thing we have to calculate. We have to move this thing across and put everything so they can cross each other. So put TF on the top and PI on the bottom. You will get PF over PI, and then move this TI along with PF. So this is how you get TF. So this is called cross multiplication. So this is another way if you want to know how to reshuffle it to get the final unit or final required answer. You can use the cross multiplication. So yeah. So now we're gonna talk about the combined gas law. So till now we just work on the laws that normally show a relationship between only 2 parameters out of the 4. But what if we have 3 parameters changing at the same time instead of 2? Then we're gonna use a new law called combined gas law, which include pressure, volume and temperature, 3 parameters at the same time, to predict the behavior of the gas, right? So we can use the combined gas law for any gas as long as the number of moles or the amount of that gas is not changing. It should not be changing, right? And then the rule tells is PIVI over TI, PFV over TF. I and F are initial and final, or you can say P1 V1 over T1, P2 V2 over T2. Again 1 and 2 are initial and final, right? Same thing. So let's try to use this combined gas law and then try to solve the problem on this. So the problem says that the pressure of 412 atm at 11 degrees Celsius, a nitrogen bubble in the skin of the diver has a volume of this. What will be the volume be when the diver ascend to a sea level at 29 degrees Celsius? So what's happening over here? You have the initial pressure, initial temperature and initial volume already given for you, right? And then you have to convert that 11 degrees Celsius to Kelvin first. And it says what will be the volume. You have to figure it out. What's your final volume be when the diver ascend to a sea level? And I know at sea level what's the atmospheric pressure, 1 atm. Even though the final pressure is not given, you should know at sea level the pressure is 1 atm. Final temperature is 29. Convert that into a Kelvin, which come out to be 302 Kelvin, and we have to use this equation, the ideal gas equation. Why? Because we are changing 3 parameters at the same time, right? And then what we need VF. So again we have to use a cross multiplication. We need VF, and whatever we need has to be in the top. They are already on the top. Use a cross multiplication. Move TF on the top and move PF on the bottom by cross multiplication. So you're gonna get this thing, And once you get this thing, plug in the value and then cross out all the unit, and then you will left with ml. So this is your answer after using the ideal gas equation. Now let's talk about the new law, which is called Avogadro's law, right? So till now we just work on the relationship between pressure and volume, volume and temperature, pressure and temperature, but we haven't used any law that use the number of moles of the gas, right? So that's how the Avogadro's law comes into play. So Avogadro's law says or tells you the relationship between volume and number of moles of the gas. So according to this law, the volume of the gas is directly proportional to the number of moles of the gas. Means if you have high number of moles, you need a bigger volume to accommodate that number of molecules of the gas, right? And the equation that we're gonna use is V1 VI Ni over Vf over Nf, or V1 over N1 V2 over N2, the same thing, yeah? As long as the temperature and pressure are constant, the other two parameter, right? So let's take an example that is given on the right side of the picture. At picture 1, you have a gas already filled in a container that has a number of moles of 1. So let's say the volume is 1 liter. You need 1 liter to accommodate 1 mole of a gas. If I increase the number of moles of the gas to 2 moles, how much amount of volume you need? You need a double of the initial volume, which is 2 liter. So this is how, as long as the temperature and pressure remain constant. So this is called Avogadro's law. You need more space to accommodate more number of moles of the gas. Let's take an example. On the Avogadro's law, it says 1.5 moles of neon gas occupy a volume. What is the new volume after adding additional 0.5 moles of neon at constant temperature and pressure? So we know number of moles, initial number of moles are given, initial number of volumes, initial volumes is given right now, and it says what's the V2 final volume after adding 0.5 additional mole. So that's your N2. So N1 we already know 1, initial volume 33, final volume, what you need to do, you have to add 0.5 moles to the initial number of moles, because it says adding an extra number of moles to the previously known moles of the gas. So your final volume come out to be 2.0 moles, right? And we have to use this equation, Avogadro's law. We need V final, we need this thing, put this thing on the top, you will get VINF over Ni, plug in the number, mole will cancel, and you will get 44.8. And it makes sense because the number of moles get increases from 1.5 to 2 moles, so volume has to get increased, right? So that's why you have more volume in here in your answer compared to 33.6, right? And it justifies the Avogadro's law. So now we're going to talk about a special condition called standard temperature and pressure condition. So we know if you're doing a experiment on the gases, under different condition gas behave differently, right? So we need to have, scientists have to come up with a standard number so that we can compare the behavior of the gas under that standard condition. So that standard condition is standard temperature and pressure. So standard condition is 0 degrees Celsius when the temperature of the experiment we are taking as 0 degree or 273, and the pressure we are taking as 1 atm. So that means we are doing a experiment under STP condition, standard temperature and pressure condition, right? And then the other term that you need to know is a molar volume. So molar volume is the amount of volume required by 1 mole of a gas. How much amount of the volume occupied by 1 mole of any gas we call as molar volume, and it is at STP. So this is important at this condition, and it always come out to be 22.4 liter. So that means if I say I have 1 mole of oxygen, how much amount of volume it will occupy? 22.4 liter, So the molar volume does not depend on the gas, which gas you are using. If it has 1 mole of a gas, doesn't matter which gas you're talking about, it will always require 22.4 liter. For example, let's take a picture. On the right hand side you have carbon dioxide gas, oxygen and helium gas at STP 0 degree and 1 atm, and then the amount of the gases present are 1 mole, 1 mole, 1 mole. So how much volume carbon dioxide need? It need 22.4 liter. Oxygen same thing, helium same thing. So it doesn't depend which kind of gas you're working with. If you have 1 mole at STP, you will always require 22.4 liter, and this number we call as molar volume. But if you see the molar mass, the mass is different, right? But we are focusing on moles and volume. So let's try to do the problem on the concept that we just learned under STP condition. So the problem says how many moles of xenon occupy 34.9 liter at STP. The time I say see at STP, I know at STP any gas, if they have 1 mole of any gas, in this case we have xenon, it should occupy 22.4 liter. And we already know the equivalency. I can make a conversion factor over here, 1 mole on the top, 22.4 liter on the bottom. Cancel it out the liter. When you solve it, you get 1.56 liter. And it's not liter, is a mole. It's a typo over there, so it's mole. So you can accommodate 1.56 moles of xenon at, if you have 34.9 liter. So it makes sense to get occupied by 1 mole you need 22.4 liter. You have 1.56 mole, you need more volume. And if you have more volume at STP, you can accommodate more number of moles of the gas, and it makes sense, right? So this is how you can solve the problem using a molar volume as conversion factor. So now we did the molar volume, we can also calculate the density of the gas at STP condition, and we know density is what, mass over volume. But instead of just mass, if I take a molar mass, this is the mass of 1 mole of a gas, 1 mole of a gas, and divide by the molar volume. This is the volume of 1 mole of a gas, 2. Then we can get the density of the gas at STP. So let's take an example, density of helium. Helium has a molar mass of 4 grams per mole, and the volume, molar volume is 22.4 liter. Why? Liter per mole. Why? Because we are taking a molar volume, 1 mole of a gas. So mole will get cancelled, you will get 0.179 grams per liter. So the density of helium at STP is 0.17 grams per liter. So this is how you can get the density at STP. Let's try to do one more problem on this density. What is the density of a carbon dioxide? Molar mass is given at STP, and you have to tell will the carbon dioxide will sink or float in the air. So we know the formula. We know the amount already given, 44.01 divided by molar volume, right? And we know doesn't matter what kind of gas we have, if I have the molar volume, 1 mole of any gas is always equal to 22.4 liter, right? That's why we use, and if we divide, you'll get 1.95 grams per liter. So the density of carbon dioxide is 1.95 grams per liter, and the density of air we already know, 1.29 grams per liter at STP. So if we compare both the density of carbon dioxide as well as air, we know carbon dioxide is heavier compared to the air. So that means carbon dioxide will sink in the air because it has higher density compared to the air. So now we're going to talk about our last section for this chapter, which is a gas mixture and the partial pressure. So what is gas mixture? Gas mixture is contain 2 or more gases within a same space, right? And then dry air is a good example. Why? Because air is a mixture of many different gases. It has nitrogen gas, oxygen, argon, carbon dioxide, and some water vapor. So they are the mix. They have different composition of different gases in there. But if I ask you about what's the pressure exerted by only by the oxygen, we know there is atmospheric pressure. What is atmospheric pressure? The total pressure exerted by the air on the surface of the earth. But if I ask you how much pressure is exerted only by the oxygen, not by all the gases present in the air, so this is a concept of partial pressure, and we're gonna learn about what is this in the next slide. So now let's talk about the partial pressure, and there is a law called Dalton's law of partial pressure, right? So we're gonna talk about this law and then try to learn what is this partial pressure means. So if we have a gas, let's say we have a container, we have three gases A, B and C, and all these gases are providing the pressure to the inner wall of this container, right? Because everything is moving randomly and then striking the inner surface of the container. So the total pressure of this container, let's assume this is PT, total pressure, right? And this total pressure is come out to be because of the individual pressure of A, B and C. I can say this thing PA, PP and then PC. So the individual pressure exerted by the individual gases on the surface, inner surface of the container where they are placed, are called partial pressure. So we assume even though the other gases are present, we don't care about the pressure of the other gas. We're just looking about how much gas pressure is exerted by only one of the gases out of the many that is present in the container, that we call as individual pressure or the partial pressure, right? So each gas we already talk about is a mixture exert their own pressure independent of the other gases, and it behave as it is alone occupied at that volume, right? And then the total pressure of that container that we have a mixture of gas present is always the individual pressure of the multiple gases, gas 1, 2, 3, 4, and then depending on how many gases you have. So this P1, P2 are the partial pressure of the gases in that mixture. So if we know the partial pressure of individual gases, we can get the total pressure of the container. Or if we have the total pressure already given, and out of the three gases that is present, if the pressure out of the two gases are given, we can get the pressure given out by the third gases, right? So we can solve the multiple problem based on this Dalton law of partial pressure. So let's take an example on the concept. A mixture of only nitrogen and oxygen has a total pressure of 3 atmosphere. So let's say you have a container, you have oxygen and nitrogen in there, and then the total pressure because of the two gases are given 3 atmosphere. If the partial pressure of oxygen is 0.63, partial pressure of oxygen is given as 0.63 atm. What is the partial pressure by nitrogen? So you have to figure it out by nitrogen. So we know the total pressure come out to be because of the individual pressure exerted by oxygen and nitrogen, and then the oxygen is already given what's in the nitrogen. So we know the Dalton law of partial pressure, the total pressure of the mixture is always equal to the combination of individual pressure, right? And we need to figure it out the partial pressure of nitrogen. We have to subtract oxygen from the mixture, so it's come out to be 2.37. So the partial pressure of nitrogen is 2.37, and if we combine with 0.60 with oxygen, we'll get the total pressure, which is 3 atmosphere. So this is how you can solve the problem on the Dalton law of partial pressure. So now we're going to talk about the Henry law. What is Henry law, and then where we can use this Henry law. So we know that in the blood, if we talk about the blood serum, we know there are different kind of gases dissolved in there: oxygen, nitrogen and carbon dioxide. But how much amount of oxygen and nitrogen and carbon dioxide gas is going to be dissolved in the blood serum determines according to the Henry law. So Henry law says or state that the number of moles of a gas dissolved in a liquid is directly proportional to the partial pressure of the gas. What does it mean? It means the partial pressure, for example, let's take about oxygen, is directly proportional to the number of moles of oxygen present in the blood. Higher the number of moles, higher the partial pressure of oxygen. And we can say the number of moles we can say as concentration of oxygen. If you have higher concentration of oxygen in the blood, that means you have a high partial pressure of oxygen. So this is how the Henry law works. So let's get to the next slide and try to see this relation one more time. So Henry law has an equation: partial pressure of any gas is directly proportional to the concentration that we learned on the previous slide, concentration of that gas. And if I remove this proportionality sign, you will get a constant called Kh, which is called as Henry constant. And this is unique for each and every gas, right? Different gas has different Henry constant. P is your partial pressure of the gas that we are talking about, and C is the concentration of that particular gas dissolved in the blood or in a liquid. Right. So pressure is always Kh over C. Right. Or you can say, you can use this equation and write something like this: the concentration of a gas dissolved in it is equal to pressure over Henry constant. I can write this thing like this way too. So that means if for any gas, we know for each and individual gases we have different Henry constant, right? Each different gases has its own Henry constant. If any gas that has a lower Henry constant, if this number is lower, that means the amount of the gas that dissolved in the blood is higher, as long as the pressure remain constant, right? Similarly, for any gas, if the Henry constant is bigger, then the amount of that particular gas dissolved in the blood is smaller, because they are inversely proportional, the concentration and Henry constant, right? So make sure you know this concept too. So now let's take an application of the Henry law and anesthetic. So anesthetic have different Kh value. The gas that we normally use to help the patient to sleep might have different Kh value depending on which gas we are using in an anesthetic. So if the Kh value for that particular gas is low or be higher, determine how quickly the anesthetic reach to a brain, right? And it also determines the time needed to regain the consciousness. For example, if you have any gas, let's say gas A, and the Kh value for this gas A is higher number, right? So that means the concentration of that gas that is dissolved is Kh, and then if Kh is higher number, that means the concentration that is dissolved for that gas in the blood is lower, and that means if the dissolved amount is smaller in the liquid on the blood, then most of the gas is can easily go to the brain, or faster go to the brain, compared to any gas that has a Kh value which is smaller. That means most of the gas that you use as an anesthetic is going to dissolve in the blood, and very less amount of the gas is available to go to the brain, right? And it will take more time, right, to help the patient to get into a sleep, right? So this is how you can predict which gas you're going to use as an anesthetic and which one you cannot, right? So now let's try to do one problem based on the concept that we just learned. We have two anesthetic, isoflurane and diethyl ether, and says the Henry constant of the first one is bigger, and is asking which anesthetic would allow an anesthetized animal to regain consciousness more quickly, the isoflurane or diethyl ether. So we're going to use the Henry law again, because it tells you how much amount of the gas is dissolved in the dissolved state in the blood. So the concentration is over pressure over Kh. So concentration of the dissolved gas is inversely proportional to the KH. So that if any gas has the higher KH value, means less amount of the gas is dissolved in the blood, and it might reach the brain faster, and vice versa too, right? Compared to the one that has smaller amount of the KH, that means more amount of the gas is dissolved in the blood, and you need more time before that particular anesthetic goes to the brain, right? And vice versa. So the larger the KH, lower the concentration in serum, and the faster the anesthetic can reach the brain, and the faster the patient can regain consciousness. So the answer is isoflurane. So this is how you can predict. So I think this is the end for the chapter number 7. Then make sure you read it through the textbook too, and then I'll see you in the next video.